I just saw an online news article video that was talking about electric car batteries, something related to batteries and lithium. I hope everybody has heard about the importance of the element lithium in rechargeable batteries, like cars and phones. And in the background of this video, I saw there were some vials of chemical compounds, or cathode is not really a chemical compound, but in the back I saw a vial with this compound, lithium carbide. You can see it here labeled in that vial, and it's this whitish gray powder. And I thought maybe I wanted to talk about lithium carbide. What is this lithium carbide compound that they've, I don't know if that's really related to car batteries, but that's what they had in their video. So when I hear the word lithium carbide, it brings me back to graduate school when I remember one of my colleagues, one of my lab mates, was trying to take acetylene. Let me draw this a little more clearly. Trying to take acetylene and was trying to convert to deprotonate acetylene in order to make lithium acetylide. And my friend was getting low yields, and he said that the problem was not the deprotonation. That was easy. I think he was using butyllithium, which is way more basic than the product, which is lithium acetylide. The problem was that it was deprotonating twice, and insoluble lithium carbide was dropping out of his reaction, which was pretty annoying, because when things are insoluble and sitting as a powder in the bottom of your reaction, that means they're not reacting. So let's talk about lithium carbide. Here is one possible chemical structure for lithium carbide. This would be referred to as the Lewis structure. And probably in the book, and probably in classes that you might have taken, you've been encouraged to draw out lithium compounds and sodium compounds like this, using lithium cations and carbanions, and then maybe lithium cations floating around. But I want to point out to you that lithium is right here in the periodic table. And the importance of that is that it is in the second row, just like carbon, just like nitrogen, just like oxygen, just like fluorine. And if it is a second row atom, then that means lithium wants to satisfy the octet rule. Lithium wants 8 electrons, just like carbon desperately wants 8 electrons, just like oxygen wants 8 electrons. And if you choose to draw lithium in this manner, lithium plus, like this over here as a lithium plus, you couldn't be further from the truth, right? If lithium really does want 8 electrons, why would you ever draw it with 0 electrons? Let's go ahead and take a closer look at the true structure of lithium carbide, because people have been trying to determine the chemical structure of this powder, of this insoluble powder, and it turns out to be this huge matrix of atoms. If you go to the Wikipedia on article, it notes the problems that they've had in growing single crystals so they could do X-ray crystallography and accurately determine the positions of those atoms. Here's what they show in that Wikipedia article. It's a reference to a picture that was drawn in a structure determination article. And it's kind of hard to make out what's going on here, right? I think you can see the lithium atoms are these black atoms right here, lithium, 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 lithium. And I think you can see the acetylenes. They're not drawing triple bonds. They're just showing that the carbon atoms are bonded together. But what are all these extra bonds here and these 3-membered rings? Over here on the side, I've tried to draw a representation where I start off with the Lewis structure. And I want you to imagine if you were a lithium atom and you wanted 8 electrons, how would you get those 8 electrons in order to satisfy the octet rule? So you can kind of see what's happening here. This lithium atom right here, over here, kind of sees this very nucleophilic carbon-lithium bond and says, hey, there's 2 electrons over there. I'm going to get me some of those electrons. Try to satisfy the octet rule. And we don't have good ways to represent this. So I'm going to show this lithium so that it's, let me use a red pen here. I'm going to show this lithium also bonded to this carbon atom with its electrons. Now this lithium over here on this other side says, well, you've got some carbon-lithium electrons. I want some of those. Okay, now we're starting to see this concept of sharing. Now we're starting to see that if each of these carbon-lithium bonds can share with a neighboring carbon-lithium bond, it gets it a little closer to 8 electrons. And each one of these lithium atoms also sees these pi electrons in those alkynes and says, hey, I'm going to get some of those pi electrons. Now, we don't have good ways to, sometimes we draw these things called dative bonds. Dative bonds are not useful for arrow pushing. You don't get the right Lewis structure. So I'm just going to draw kind of plain old everyday single bonds here, right? If that lithium really does bind to those pi electrons, it will be bonded to both of those carbon atoms. So each lithium atom starts to get some electron density. And you can imagine if you've got another acetylene molecule that I didn't draw sticking straight up and down, that same lithium could get 2 more electrons by bonding to, well, that last bond didn't look so much like a 3-member ring. You can get some more electrons by bonding to another acetylene atom. And so that's this complex structure. Each lithium atom is desperately trying to fulfill the octet rule, right? When you draw lithium as lithium plus, that's not what's going on in solution. We've been lying to you from the day you started probably general chemistry about the true nature of sodium and lithium, certainly lithium. Lithium wants to satisfy the octet rule. And I'm not saying that's wrong to lie to you, because once you start drawing all these bonds to lithium, it turns into this crazy mess that is very hard to keep track of. So it's well-intended lying. Sorry, I'm trying to pick up where we left off. Okay. We have an exam coming up on Friday. Everybody should know that. This is exam 2 coming up. And the exam will cover chapters 17, 18, 19, and 20. Those are the acyl, the carbonyl addition chapters. Remember chapter 17 was Grignard addition to carbonyls and lithium aluminum hydride addition to carbonyls. Chapter 18 was the addition, condensation with carbonyls, making imines, making enamines, making acetals, cyanohydrins, and then some Wittig chemistry thrown in there. 19 was carboxylic acids in addition to nitriles, addition to CN triple bonds, which in some ways resembles the reactivity of addition to esters. And then chapter 20 was full of transformations of carboxylic acid derivatives. Acyl chlorides, making amides, making esters, hydrolysis of esters, hydrolysis of amides. We gave you a bunch of that stuff, making amides using DCC. So there's a lot of material, and you really have to practice those reactions. You got a couple more days to practice those problem-solving tools, and I'm going to give you lots of problems on the exam to solve. Let's step back into chapter 21 here. Chapter 21 is not on our exam. This is the next exam, the third exam we're going to be covering this. And chapter 21 is about deprotonating alpha to carbonyls. That's what we've been doing in this chapter. We almost finished chapter 21 here. I didn't quite get to the end of that in our last lecture on Monday. So in this chapter, we've been deprotonating next to carbonyls and then doing, when possible, doing SN2 reactions, using those enolate intermediates to do SN2 reactions. That's the big theme for this chapter. And then I showed you that if you have a carboxylic acid, and you have to look really carefully because I'm not always going to orient the molecules in the same way. If you have a carboxylic acid that has a keto group, not at the alpha position, but here at the beta position. If there's a carbonyl off of that beta carbon, that carboxylic acid is susceptible to decarboxylation. You can lose a carbon-carbon bond, you can lose carbon dioxide, and it generates an enol. And enols are not stable. You cannot stop that enol from isomerizing into a ketone form. We learned this back when we learned about addition of water across triple bonds. You get these enols that spontaneously, without your permission, will isomerize relentlessly in order to give you the keto form. So that decarboxylation seems a little bit mysterious, and it goes through this 6-member transition state, that decarboxylation process. And this is the process that your human enzymes use in order to make carbon-carbon bonds. Your body makes enolates using this decarboxylation process and then uses those enolates for CC bond formation. All right, we are almost done with chapter 21. I got one last very similar thing to talk about, very similar to the malonic ester synthesis. So malonic ester synthesis, great for synthesizing barbiturates. That's not really that popular anymore. Unfortunately, our lab still has to carefully control our malonic acid. They're so afraid we're going to like sneak in and make some barbiturates in the weekends, which is... it's just kind of ridiculous. Okay, the acetoacetic ester synthesis is very similar to the malonic acid synthesis. The malonic acid synthesis, we had esters on both sides. And the acetoacetic ester synthesis is very similar. You've got a ketone on one side and then an ester on the other. And otherwise, it's very similar. We choose a sodium alkoxide base that has to match the ester because we don't want to end up with some problematic, I'll talk about this more in the next chapter, we don't want to end up exchanging a methoxy ester for an ethoxy ester or something. So we always make sure that the alkoxide base matches the ester. So use sodium ethoxide for methyl esters, use sodium ethoxide for ethyl esters. And I told you already, this proton between two carbonyl groups is so acidic, it's more acidic than water. Once you make the enolate out of this, you can just dump it into water and it'll sit there and it won't get protonated. Those enolates are so stable, they were able to use them back in the 50s and 60s. With very little technology. So this idea here is that you deprotonate at this alpha position right here. You make an enolate anion, and then you do an SN2 in the next step. So let's go ahead and take a look at the product of that process. This would add another alkyl group here at that alpha carbon between the two carbonyls. So this compound here would be called methyl acetoacetate. Right? If you just had this part of the molecule, it would be methyl acetate. If there's an extra acetyl group, that will be called acetoacetate. And this one has two alkyl groups on it. It has the ethyl group that was there in the beginning, and it also has the methyl group. And you would get a mixture of 2 enantiomers out of this. I'm not sure if it's that important just for this transformation, but we'll go ahead and note the presence of a stereogenic center and the presence of the stereoisomeric mirror image of that. So I'll just write plus E. Now, sometimes we don't want this extra ester molecule. And so here's what you can use. You can hydrolyze that to the carboxylic acid and using acidic conditions. And the carboxylic acid that you get by hydrolyzing the methyl ester will spontaneously lose CO2. So what are our conditions for acid hydrolysis of esters? You can use sulfuric acid or you can use HCl. And then we do these in water and we heat them. So there is an intermediate here that we don't have to draw out, and that would be the carboxylic acid. The byproducts of this process would be CO2, but we don't isolate that because it's just going to blow out of our reaction as gas bubbles. And the other product of the reaction is methanol, which is so volatile that would just come off when we evaporate our solvent for the reaction. Okay, so if you're trying to make new carbon-carbon bonds, and it was the 1960s, this is a good way to make this carbon-carbon bond. Now, I've shown you a powerful way to make carbon-carbon bonds, and that's using lithium enolates. But this is actually pretty clever because I can't make that product using LDA. Let's talk about the problem. Let's suppose I started off with a ketone that had a methyl group on one side and an ethyl group on the other, and suppose I wanted to specifically add a new methyl group to this carbon. I can't do that with LDA. It's not that LDA is not strongly basic. It's not that LDA doesn't give enolates and quantitative yield, but I want you to recall that if you take LDA and you make enolates, LDA will deprotonate on the least hindered side. Here's the least hindered side. It's the methyl side. That side with the propyl group is not the least hindered side. So you'll get 100% yield of that lithium enolate. And so that's where you're going to alkylate. When you do an SN2 reaction using methyl iodide, you're going to get the new carbon-carbon bond on the other side. So we don't have a way to easily, that I'm going to show you that is, we don't have an easy way to put that methyl group over on this other side. You don't get the new methyl group on the more substituted side when you do LDA chemistry. So that's maybe one place where this acetoacetic ester synthesis could be valuable for putting a methyl group on the more hindered side. But that acetoacetic ester synthesis is now, we have tricks now to avoid using this acetoacetic ester synthesis because heating things in acid is not super ideal for organic chemistry. Lots of functional groups will fall apart. All right, that's the end of chapter 21. So what was chapter 21 about? Chapter 21 was about making enolates and then using them for SN2 reactions to displace things. But we're going to go ahead and move on now to chapter 22, which you're going to say, isn't this kind of the same as chapter 21? Yeah, it's got a lot of similarities to chapter 21. Okay, here's chapter 22. So in chapter 22, we're going to be making enolates. And instead of doing SN2 reactions, we're going to add those enolate carbanions to carbonyl groups. Kind of fits with the theme of this quarter. You know, we kind of start off the quarter after the electrophilic aromatic substitution stuff, adding every nucleophile in the world to a carbonyl group. So I hope it makes sense that when we make enolates, we're going to be adding them to carbonyl groups. So let's go ahead and take a look at this. Here's this reaction that is the centerpiece for chapter 22, and it's called the Aldol reaction. Aldol reaction. Aldol is kind of a combination of the name aldehyde and alcohol. The starting materials are aldehydes. In the product, you get a new alcohol. And so you can see what's going on here is you're taking a carbonyl group, and at that alpha carbon, it's making a new bond to another carbonyl group. And there used to be an H over here on this position, and now that H is now gone, and it's somehow you've gotten a new H over on the oxygen that used to be the carbonyl. All right, let's go ahead and talk about what's going on in this reaction, this Aldol reaction. The mechanism is going to start off with deprotonation, and traditionally conditions for these alkoxide promoted aldol reactions is that you deprotonate with the alkoxide base in order to make an enolate. And you could use sodium hydroxide here. You don't have to worry that much if it's just an aldehyde or a ketone about whether it's hydroxide or ethoxide or sodium methoxide or potassium T-butoxide. We're just using the OR as a base to deprotonate and make a small amount of enolate. You get a little bit of enolate out of this. You don't need a high 100% yield of enolate. You just generate a small amount of this enolate intermediate, and enolates are powerful nucleophiles. This is actually equilibrium, right? You generate a small amount of this enolate. There's two possible resonance structures. I'm going to draw it as the carbanion resonance structure instead of the enolate resonance structure, because then it makes it obvious which of the atoms here is the nucleophilic atom. It's the carbon atom. Now, we don't do reactions on one molecule. I don't have a way to put one molecule in a flask and then do a reaction on one molecule at a time. We pour 10 to the 23rd molecules in our flask. So let's just take it as a given that if we're only generating a tiny amount of this enolate, then we still have lots of aldehyde molecules floating around and colliding with that enolate. 10 to the 23rd molecules are floating around in that flask, and only a small amount of them are deprotonated as enolates. So there's definitely going to be more aldehyde molecules floating around, and that gives this the opportunity to do something super satisfying. Attacking carbonyls. Boy, that's what this next exam on Friday is going to be about. Things that react with carbonyl groups. So now that we know about enolates, it should be really satisfying to take those enolates and add them into carbonyl groups. And that's the Aldol reaction. So when we do this, we generate an alkoxide initially, because that carbonyl group that we added to now has an O- there. And remember when we initially protonated or deprotonated using our alkoxide base, we could have written the symbolic base B here. I just wrote out explicitly alkoxide and then use HB over here to do the protonation. But since I wrote out alkoxide from the start, I better use HOR as my conjugate acid. And that's the mechanism. Ooh, let me use a black arrow for that last reaction step. Okay, that's the three-step mechanism for the Aldol reaction. Now, you notice I just created two new stereogenic centers here. And you'd have no control over those. You'd end up with 4 different diastereomers. I'm not going to draw all of them for you. It would be like wedge, wedge, dash, dash, wedge, dash, dash, wedge. I'm not drawing all those for you. You just get a bunch of stereoisomers. We're just focusing on the mechanism here. Okay, make an enolate, add it to a carbonyl. And that's really the whole chapter. So we're just going to do that over and over again until you're sick of it, and you can answer every problem on my exams. Now, why are people so interested in this reaction? Because when you go to nature and you isolate molecules out of plants, out of sea sponges, out of trees, out of microorganisms in the soil, there is invariably one class of compounds that tend to have potent biological activity, and I'm going to show you an example of one of them. This is a molecule called, that was isolated by 2 groups from sea sponges. Why would they go explore sea sponges? Who would do that? Turns out that's a job. Natural products isolation chemists. And sea sponges are delicious if you're a fish or some sort of sea organism. So if you're a sea sponge and you don't want somebody to eat you, and you don't have arms and legs to fight them off, you better produce some really toxic compounds that kills everything under the sun. And so sea sponges are good at producing things that are just amazingly toxic. Lots of seemingly helpless microorganisms produce devastatingly toxic molecules that are so inventive in their mechanism of action that chemists and biologists could never reproduce that. So we go isolate those molecules from nature. This one has a IC50, that's the dose it takes to kill 50% of cancer cells. Oh, so why is it interesting to kill cells? Well, if you're good at killing predator cells, then you're also good at killing cancer cells. So people are really interested in molecules that can kill rapidly dividing cells like cancer cells. And this molecule is one of the most potent known anti-cancer molecules out there. It's got an IC50 of 20 picomolar. I don't even know, what's a pico? So I know what nanomolar is. That's like 10 to the minus 9. Picomolar is just crazy in terms of the potency, the small amount. Even though it only takes a tiny, tiny amount to kill rapidly dividing cells like cancer cells, you're not going to be able to dive under the ocean and isolate enough sponges to treat cancer patients in the United States. So anybody who wants a supply of this molecule is going to have to synthesize it from scratch. So synthetic chemists set out to synthesize this, and this looks absolutely bewildering. It's like, how am I going to make this using things that I learned in Chemistry 51C? But I want to remind you that I just taught you this Aldol reaction. This Aldol reaction teaches you to make a bond at the alpha carbon of a carbonyl. And so once you know how to make this carbon-carbon bond right here, well, you know how to take carbonyls and convert them into acetals. So anytime you see a hydroxy group beta to an acetal, well, you could do an aldol and then make an acetal. And when you look at this molecule, you can see hydroxy groups, right? Those hydroxy groups that are over here, beta to acetals. Here's a hydroxy group, beta to an acetal. Here's a hydroxy group, an alkoxy group. They're both beta to an acetal. Every time you see an alkene that is beta to a hydroxy group, that could have been made through a Wittig reaction. You do an aldol, then you do a Wittig reaction. Or if you do an elimination reaction of this hydroxy group, you can get an enone. So everywhere you see some sort of an enone or a hydroxyalkene, all of those could be made by first doing an aldol reaction. And so the chemists that set out to make this said, oh, I know how to make this. I'll do an aldol here, an aldol here, an aldol here, an aldol here, and then I'll follow that up with Wittig reactions and acetal-forming reactions. And they were able to know, they're well within the means of synthetic chemists nowadays who have taken a class like this to go in and synthesize this molecule. They have to know how to put on some protecting groups, like those silo protecting groups along the way. But this is a molecule that's been made by synthetic organic chemists, and molecules more complex than this. So why does this chemistry work so well? It works so well because this is how the microorganism makes these molecules. Microorganisms are making these molecules, the CC bonds, using aldol reactions. That's why you end up with this functionality with oxygenation 3 atoms away from each other. Okay, so let's talk more about this aldol reaction. And specifically, I'm going to talk about a version of the aldol reaction, a transformation that involves 2 stages that is called the aldol condensation. Anytime you hear somebody say the word condensation, it means that water is being given off as a byproduct. You're condensing 2 things together to give off water. So here's the aldol condensation. You take a base, like it could be sodium methoxide or sodium ethoxide or potassium T-butoxide. This one, they're using sodium hydroxide. And under the conditions of this reaction, you initially get, I'm not going to draw the whole mechanism, the 3-step mechanism, but the product you would get from this aldol reaction. Boy, you need to be good at seeing aldol reactions. You need to practice this so many times so you can see, oh yeah, I'm going to form a bond there. And then I expect you to draw out the aldol product. Lickety-split and not hesitate. Practice enough reactions where it's like you can see exactly what that aldol product is going to be. No matter how I twist the molecules around or draw it in a different orientation, you should practice enough aldol transformations to be able to draw out the products reliably. Now, this is just an intermediate. Under the conditions that I've shown you, you don't stop here. This keeps going. In fact, there's a proton here, and there's an OH there, and under the conditions of the reaction, this can lose the elements of water. It can do a dehydration. You already know how to do dehydrations. Now, let's just be really careful here, because I tell you on my exams, please clearly indicate stereochemistry and the presence of stereoisomers, if any. Clearly indicate stereochemistry. Well, I don't see any stereogenic centers in here. Well, how am I going to draw dash or wedge, or why does it? There is stereochemistry here, and it's not dash, wedge, and RNS. It's the alkene can be cis or trans, and you have no control over that. Well, you usually get a little more trans. So this would actually be present as a mixture of E, this is the Entgegen or trans isomer, and Z isomers. So this is one of those unfortunate things where if I ask you to clearly indicate stereochemistry, you'd have to note that in this reaction you get both the E and Z isomers, the cis and the trans. You'd get a mixture of those. You don't control that. Now you know how to do elimination reactions from back in the first quarter of organic chemistry. We taught you how to take alcohols and treat them with sulfuric acid, and you lose water. That goes through a carbocation. There was also this kind of obscure reaction with, I think, POCl3 and pyridine or something like that you could use to eliminate alcohols. But so this is a different kind of reaction, and the mechanism is one you have not seen before. It doesn't go through E1. It doesn't go through E2. It goes through a mechanism that we describe as E1 conjugate base. E1 conjugate base. It's not E1 mechanism. It is not E2 mechanism. And the E1 conjugate base elimination mechanism is the most common mechanism for elimination in organic chemistry. So why did we wait to the end of the course to teach it to you? I don't know why. That's just the way the book is designed. So let's talk about this. If it's such a common mechanism for elimination of water from reactive intermediates. Oh, I forgot to mention up above here. Why didn't this stop at this hydroxyaldehyde stage? It's because of this. There was heat in here. And on the previous slide, I didn't show heat, but now that we're heating it, that's what's driving elimination. If you do substitution reactions and you heat those reactions, you get higher amounts of competing E2 elimination. So when you go in the lab and try to do SN2, you try not to heat those reactions up because the ratio of elimination starts to increase as you heat up reactions. So it's the heat that's really favoring that here. Now let's go ahead and draw out this mechanism for elimination. It doesn't involve carbocations like an E1 reaction. It doesn't involve a concerted deprotonation, and I'm trying to figure out where's my black pen here. It doesn't involve a concerted pull off the proton and the leaving group leaves at the same time. Right? We've got a proton here that can be pulled off by a base. We've got to remove that proton because we start off with 2 protons there and we end up with 1 in the alkene. So a base is definitely going to need to come in here and pull that proton off. There's the base. It's going to pull the proton off. But the issue is, what are we going to do with that pair of electrons? Well, you already know what bases do to protons that are alpha to carbonyls. This is the preferred event here, is the electrons go into the carbonyl. They don't push out the hydroxide. That would be E2 elimination. They make an enolate. They make some kind of an anion. And that's what makes this E1 conjugate base. You make some kind of an anion in the first step of the mechanism. And we know how easy it is to form enolates. We just did that in the previous reaction, the Aldol reaction. So if it was facile to make enolates in the Aldol step, it must also be facile to make enolates on that product. So now we have this intermediate that has this carbanion. Here's this carbanion. There it is. Wow, carbanions. I mean, it's a stabilized carbanion because it's an enolate. And it doesn't matter what resonance structure I draw. Maybe I'll try to get to that. So now we've got a leaving group next door to this carbanion. And you might say, wait a second, I was told that hydroxide can never be a leaving group. That's in SN2 reactions. This isn't SN2. That's right. You can't have hydroxide or alkoxide act as leaving groups in SN2 reactions. But this is no SN2 reaction. There is a carbanion next door all the time, can't get away, always donating into that antibonding orbital, and so there is no problem pushing out this hydroxide leaving group. It could be alkoxide, it could be, well, I keep looking for my black pen here, it could be T-butoxide, no problem pushing out that leaving group. If you've got an O- next door, a C- next door, an N- next door, that hydroxide is out of there. That's the two-step E1 conjugate base. This thing right here, this is the conjugate base of the starting material, right? When you pull off a proton, you get the conjugate base. And I could have drawn this mechanism as proceeding through the resonance structure. I'm not going to draw all the arrow pushing to get to this, but I could have drawn this resonance structure as my enolate. And it's the same thing. Whether I draw, it doesn't matter what resonance structure I choose to draw for that enolate, you're still going to push out that hydroxide. Here we go. Those pi electrons are super nucleophilic because they're next to that O-, and that pushes out the hydroxide. So these two are the same thing. How can I draw this? I'll draw kind of an equivalent sign. These mean the equivalent thing. They mean the same thing because I'm taking a resonance structure and just doing the same transformation with that. So you can choose which of those two ways you want to depict that. This is going to be really hard for you to get used to this E1 conjugate base. Right? After how many months have you been practicing E2, which is a concerted elimination? Right? This is not concerted. Right? If you simultaneously push out the hydroxide while you're deprotonating, that's E2. And these things don't eliminate in one step. It's a two-step mechanism. So it's going to be tough for you to get used to this. And we don't have a lot of time to practice that, but that's going to be essential for this chapter and for the rest of your experience in organic chemistry to get used to E1 conjugate base mechanisms. Now, this whole idea, it's like if you've been watching closely, it's like, wow, well, I mean, if I take some sort of aldehyde like this propionaldehyde or propanal, and I treat that with some sort of a base, how am I going to know whether it's giving me elimination or not elimination? Because on that first page I showed you, you take sodium hydroxide and you get this aldol product. It's got a hydroxy group and it's got an aldehyde group and it's an aldol product. But then I told you also that you can get elimination, and the book shows you these two reactions and doesn't tell you anything about how to anticipate whether it's going to eliminate. They show you sodium hydroxide, sometimes they draw the enal, and then sometimes they draw the hydroxyaldehyde. I'm the one who's telling you that in my class, if I draw heat in an Aldol reaction, you should assume it's going to do the elimination. And we call that an Aldol condensation when it eliminates water. And if I don't show the heat, except for the situation I'll show below, if I don't show the heat, then simple alkyl aldehydes will stop at the hydroxyaldehyde stage. But I'll give you one exception down below, where you get elimination whether you heat it or not, whether you want to or not. Okay, molecules love to have conjugation. So let me go ahead and draw a situation where whether you want it or not, you're going to get elimination, even if you don't heat it. And the book even tells you this. They say the Aldol reaction will be followed by spontaneous elimination if the new CC bond, that's like if this new bond ends up conjugated to some other double bond, it will spontaneously eliminate. The elimination will be so fast you can't stop it. Let me go ahead and jump forward to show you an Aldol reaction that's a little bit mysterious because it doesn't involve an aldehyde. It involves two ketones, but it's the same idea, right? If I take something that can form enolates, the enolates will start to add back into the carbonyls. There's lots of molecules in this reaction flask. There's 10 to the 23rd molecules floating around in this reaction flask. Once you make a tiny amount of this enolate, right, like right here, once you start to make a tiny amount of that enolate, you can't really stop that from adding in and doing aldol reactions. This is why keto-enol tautomerism is not interesting under basic conditions. Nobody cares about enols when you start treating ketones with base. All of a sudden you're going to start getting aldol reactions, and that's the thing that your attention will be focused on. And so in this product that you get, the product that you get out of this reaction, even if you don't heat it, so let me go ahead and draw it as our reagent here. The reagent here would be sodium hydroxide or sodium, just to be different, I'll put sodium ethoxide, but it could be sodium hydroxide. And then the product that you get has that new double bond, not the carbonyl, don't worry about the carbonyl, but the new double bond is now conjugated to another phenyl. And I'm going to draw it out so we can see that conjugation. See that conjugation there? That double bond is now conjugated with the new double bond of the enone. So it's this conjugation right here. Let me be specific about this. It's this conjugation that tells you that this is going to, all right, that conjugation right there tells you that it's going to be, that the elimination will occur even if you don't heat it. There is conjugation with the phenyl and the ketone, but that's not what determines whether the aldol is spontaneous. It's all right. That conjugation means spontaneous elimination by that E1CB mechanism. Okay, so the aldol condensation makes enones. Why is that cool? Most chemists don't want to generate. Remember I told you that the aldol condensation generates mixtures of stereoisomers? I told you over here that, right, this can be wedge, wedge, dash, 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 wedge, wedge. Organic chemists don't like mixtures of stereoisomers. And the enone products have fewer possible stereoisomeric possibilities. So, and once you make an enone, well, now we can do dihydroxylations, epoxidations. We can add nucleophiles to the aldehyde. We still have an aldehyde functional group. We can hydrogenate the alkene down. So having that alkene functional group is pretty valuable. Very useful. Okay, it's going to be kind of tricky for you to start recognizing aldol reactions. And I want to point out that if you take benzaldehyde and you try to do an aldol reaction, right, and this may seem so obvious to you, but once I start drawing things like this, you'll be thinking, oh yeah, I'll just deprotonate next to the phenyl. But these are the same molecule. I've just drawn it in different ways. Right? These are the same thing. And there is no alpha proton in this carbon. And there isn't even an alpha carbon on the other side, so how can you pull off the alpha proton from the other side if there isn't even an alpha carbon? There is no way to do an aldol reaction on this. You can't do any kind of aldol chemistry. You can't make any kind of an enol 8 intermediate. It's not going to happen. And you've got to watch for that. It's like you've got to be sure that there's going to be an alpha carbon and protons on the alpha carbon, or we're not talking about any potential for aldol reactions under there. Okay, as I mentioned in the last slide, ketones do have alpha protons. I'm showing you acetone. Why is that a good one? Because both sides are equivalent. It's methyl on one side, it's methyl on the other, and you don't have to worry about, well, which side am I going to form enolates on? We tend to pick things where there's only one possible enolate, and if it's a symmetrical ketone, there is only one possible enolate. And this would be an example where once you make that enolate anion by deprotonating, you can then get that. So here, if you deprotonate that ketone, the acetone, then you'll start to do enolate chemistry. I'm trying to keep forgetting my black pen here. So once you make the enolate, there we go, there's the enolate. You can come back in and add to another carbonyl. I'm going to reorient this so it's easy to see how this maps onto the product. And then there's all these extra steps with E1 conjugate base for that conjugation. I can't remember whether that's 3 or 4 steps. You add, you protonate, you deprotonate, eliminate. What is that? Add, deprotonate. 4 steps. 4 mechanisms. And I'm not going to draw those out. Okay, so as long as you've got alpha protons, you can do these aldol condensations, whether you've got ketones or aldehydes. So even though it's called an aldol condensation, you can also do it with ketones, which aren't aldehydes, is the idea. All right, yeah, so we still call it the aldol condensation. You're going to have to practice this. Here's some examples. You've got to practice this. I expect you to be able to work aldol reactions and aldol condensations backwards and forwards. Right? If I give you this product here and I say, I want you to tell me how to make that, my hope is that you will have worked enough problems to say, oh, it's an enone, aldol. I mean, that should be totally obvious. After you've worked enough problems, you'll say, oh, I can make that through an aldol. And you need to identify what are the 2 pieces I would need to mix together in order to make that through an aldol. Well, all I would need is just to take cyclohexanone and some sort of a base, sodium hydroxide or sodium ethoxide. Now, when I draw cyclohexanone, there's more than one molecule in the flask. I don't have to draw 2 molecules, but I'll go ahead and do it for you. Obviously, there's more than one molecule, and here would be the other one. So this If you just took cyclohexanone and treated with sodium hydroxide, and then we heat this, we want this to eliminate, then we'll get the Aldol condensation reaction. Right? Come back a day later and you'll have this enone product in there. You're going to have to practice that, right? It's not going to come to you just by maybe working one problem or looking at my notes here. Here's another enone. I can see that so clearly. Enone, look at that enone there. Boy, I know that came from an Aldol reaction. So let me faithfully trace through. In the Aldol reaction here, I'm generating this new carbon-carbon bond, the double bond, through a CC bond-forming Aldol reaction. Here's the CC double bond, and you're going to have to work enough reactions so that this intramolecular Aldol reaction is obvious to you. Let me go ahead and draw those two pieces. The Aldol reaction always involves some sort of alpha protons, and it always involves some sort of a ketone that turns into the double bond. And you're going to have to practice this enough to where you can see that this Aldol starting material looks like this. That's going to take some practice. Boy, that's not a well-drawn O here. Let me draw that O there. And so you can kind of see, so I must have had a CH3 group over here at this position that formed an enolate and then condensed with that carbonyl. And again, what are my conditions? I could use sodium hydroxide. Just to be different, I'll choose sodium methoxide. Doesn't matter for these ketones and aldehydes. And this one, see the new double bond here? Is conjugated. So I don't actually have to heat this. I could if I wanted. No problem if you show heat. But the double bond here in the phenyl ring, that's conjugated. So I don't need to heat. But I could if I wanted. So heat, not, that's a delta symbol, poorly drawn. Boy, that's not necessary. So the heat, you don't have to heat that, but you could if you wanted to. All right, so, boy, look at that. Isn't that crazy looking to have to think backwards to an acyclic substrate when the product is a ring? I think this last one may be a little bit easier, except you can see how crazy things can get once I start reorienting the bonds. And here I purpose, not to be a jerk, but just a lot of times chemists draw whatever's easy to draw using ChemDraw drawing program. And maybe it would be easy to see if I oriented this ethyl group down here, but instead I've oriented it kind of along the carbon-carbon backbone. Right? It's not always going to be obvious to you what is the, let me take this off. It's not always going to be obvious to you that this was a product of an Aldol reaction. Right there, that bond, that CC bond right there can be formed easily through an Aldol reaction. And maybe it would be even more difficult if I didn't write ET twice. What if I drew it like this? Ethyl, hydroxy, and then I drew one of these as ET, and now maybe it might not be so obvious that both of these pieces came from 4 carbon aldehydes. So let's go ahead and draw those 2 aldehyde pieces here. Here would be one of them, an ethyl group, and then a carbon and an oxygen. Remember, the ethyl has 2 carbon atoms in that ethyl group. So, and this is all. I don't need to draw 2 molecules of the aldehyde. You could, I suppose, in here, or write 2 equivalents, but that's not even necessary. And I'll just write sodium hydroxide here. I'm not going to heat it. Heat would give the elimination product. Okay, so that would be the conditions for making that aldol product. It's just sodium hydroxide, and that's called butyraldehyde. It was the old-fashioned name. Butanal is the IUPAC name for that aldehyde starting material. And of course, there's more than one copy of the molecule present in solution. If there was another reactant in there, I'd probably have to pay attention to stoichiometry. 2-to-1 ratio, 2 equivalents, but there's only one reactant, so you don't really talk about number of equivalents if there's only one reaction. Okay, I'm going to stop right there. Let me just take a peek at what's coming up next. When we come back, so what's coming up next? Your exam is coming up next on Friday, so you can think more about these aldol reactions next week, but study the heck out of these Grignard reactions, acylation reactions, esters, amides, nitrile additions to nitriles, Wittig reactions, imines, enamines, all that stuff. I missed, I don't know, I just spaced out and I missed my study hall on Monday night, so I've moved that to Friday morning. My extra study hall. We have extra study halls for you this week.